All right, good afternoon. Let's continue with our discussion of FETs. We'll wrap up, well, most of the introduction chapter, and then next week we'll look at applications. Not next week, sorry, from next class onward. Okay. So we'll look at the basic device physics to how to establish a channel in a MOSFET and how current would flow through. So again, this is a brief recap. Essentially, we have either two N-type regions or two P-type regions. They are separated by a certain distance. When we apply a voltage, we can create a channel that joins or links these two regions. Once the channel is available, we can apply a voltage or potential difference between these two regions and current would start flow. If it's two N-type regions, we create an N-type channel. If it's two P-type regions, we create a P-type channel. And so that's the name of the device, N-channel MOSFET and P-channel MOSFET. This particular example was about an N-channel MOSFET. The three terminals are known as the gate, the source, and the drain. The drain and the source are the two N-type regions. The gate is the controlling terminal. Current flows between the drain and the source. So similar to a BJT, you have a three-terminal device. Current is flowing between two terminals, and a third terminal is used to control the flow of current. In this device, there is no, the base terminal, not the base, the controlling terminal doesn't send any current into the device. Okay, it's a voltage control device because that third terminal, the gate, is separated from the drain and source or from the entire device by a thin layer of insulating oxide material. Right, so no current actually flows into the device itself. It's all voltage controlled. Now, in order to establish the channel that links the drain and the source, we need to apply a certain voltage. Because the voltage needs to be applied externally, this is known as an enhancement mode MOSFET or an enhancement mode device. If a channel existed due to fabrication itself, meaning there is no voltage required to be applied, then it is known as a depletion mode device or a depletion mode MOSFET. In this case, a voltage would need to be applied to turn the channel off. Okay. So again, our discussion is with respect to enhancement mode devices, not with depletion mode. So in an enhancement mode device, we apply voltage between the gate and the source. When you apply a voltage between the gate and the source, this creates a channel right underneath the gate that links both the drain and the source. When the channel is established, as shown here, and we apply a voltage between the drain and the source, well, the channel has electrons. If you apply a positive voltage in the drain with respect to the source, these electrons will move in response to that applied external voltage. And so you have current, electrons flowing from the source to the drain, current flowing from the drain to the source, similar to a BJT. All right, so based on these conditions, we have three modes of operation. When the channel does not exist, the device is cut off, right? And you slowly start to increase the voltage, electrons are pulled forward, channel starts to form. The minimum voltage, the minimum level of voltage for VGS that is required to establish the channel is known as a threshold voltage. That is the minimum threshold level that the VGS needs to overcome. And so VGS must be greater than the threshold voltage VTN. Okay. Any voltage in excess of VTN is known as the gate overdrive voltage because we refer to it as the gate being overdriven. Okay. Any voltage that is applied at the gate source, VGS, in excess of the required threshold voltage is known as the gate overdrive. Obviously, if it's exactly equal to the threshold voltage, idea is theoretically it should turn on, but it must be slightly greater than the threshold voltage. So if threshold voltage is 1, theoretically we would say we want VGS slightly greater than 1 volt. Delta VGS is the notation for the gate overdrive voltage. So it stands to reason that delta VGS must be positive. If it's negative, that means VGS is less than the threshold voltage, the device is cut off because there is no channel available. All right, so it must be positive to turn the device on. And that corresponds to this region right here. So when there's no channel, VGS is less than the threshold voltage, device is said to be in cutoff. Cutoff for a MOSFET and for a BJT is the same region, close to the y-axis, close to the x-axis, where increasing VDS does not result in increasing current, right? Doesn't matter how much you increase VDS, current remains close to 0, cutoff region. As the channel is established, the voltage and current would have a linear relationship, right? And that region is known as the linear or the triode region, and which is indicated here. Okay, channel is established. You apply a positive voltage for VGS and a positive drain voltage with respect to the gate. However, what happens when you apply, this is N-type, this is P-type, right? So if you apply a positive voltage at the drain with respect to the source, we are also reverse biasing this junction right here. And because we are reverse biasing, the depletion region right around here keeps on increasing. And the depletion region keeps on increasing, meaning when VDS increases beyond that level, that means VGD drops below the threshold voltage, then the channel begins to pinch off right here in this area. When the channel pinches off, we would actually expect the current to go to 0. But that is not the behavior that is observed. What happens, in fact, is that there is a small gap left where the electrons are now flowing at a constant rate. They are now injected into the depletion region. And because there is a large electric field, they are swept through the drain terminal. And this flow of electrons remains at a near constant level. And this is verified with the fact that the current ID, the drain current, flattens out. Okay, so before the channel pinches off, the relationship between the drain current and the voltage is linear, so it behaves like a resistor. Channel behaves like a resistor, voltage control resistor. But once the channel pinches off, meaning VGD drops below the threshold voltage, the current becomes almost flat, constant rate. So similar to a BJT, it behaves like a constant current source. So BJT has terminals collector, base, emitter. We can make a certain kind of analogy between the FET and BJT, where you have the drain, the gate, the source, and the drain, right? In the BJT, we have the output collector current, IC. In the MOSFET, we have the drain current, ID, as the output current. BJT. Oh, yeah. So the BJT behaves like a current source, but it's controlled by the base current IB. So BJT can be modeled as a current controlled current source because it's controlled. The output current is controlled by the base current IB. So it's a current controlled current source, whereas a MOSFET or an FET is a voltage controlled current source. BJT is primarily a current control device. A FET or MOSFET is primarily a voltage control device. Application of electric field, field effect transistor, right? And so that region is known as the active or the saturation region. In a BJT, the region to the left was known as the saturation region. In a FET, in a MOSFET, the region to the right is known as the saturation region. So again, in BJTs, active and saturation regions are separate. In MOSFET, the active and the saturation regions are the same. Okay, so the three regions of operation, we can simulate the functioning of a MOSFET in LT-SPICE or in P-SPICE, obtain a set of data points and extract the information about the threshold voltage and other parameters from that data, which was also one of the procedures in that lab, right? Well, the first procedure in that lab, which is where you apply a VGS, gate source voltage, and you sweep the voltage between the drain and the source, obtain a set of data, and we can extract information about the threshold voltage for that device. So we can do that. We can do that by applying voltage at the gate and at the drain. So VDS and VGS. So if we know that the threshold voltage is 2 volts, we must apply VGS in excess of 2 volts, right? If you apply 2.1 volts, then the gate overdrive voltage is 0.1. If you apply 2.8, as shown here, then the gate overdrive voltage is 0.8, which is shown to be right here. This is a plot of output drain current as a function of the drain source voltage VDS. Okay. If you wish to extract the parameters from the output characteristic, we can take a MOSFET. There's a MOSFET model 2532, I believe. Yeah, 2532. Apply VDS, apply VGS. We are sweeping VDS from 0 to 10 volts in steps of 0.1 volt each, about 100 data points. And VGS is swept from 4.5 to 5 volts in steps of 0.5 volts each, meaning it's only 2 steps, 4.5 and 5. Have you all used this command before? Dot step param. This can be used for any component. Okay, so here we are using it for a voltage source. We are sweeping the DC voltage source, right? We can use it for variable resistors, capacitors, inductors, for anything actually. Dot step param X. X is the value of the resistor, and then you can define the different values for that resistor. And so it will simulate, LT-SPICE will simulate all those values. Anyway, so we obtain 2 sets of data curves, 4.5 and 5 volts. This is a plot of VDS. Sorry, this is the plot of ID as a function of VDS, output current as a function of the applied voltage. And so here, if you see, this is closer to 1.1 and 1.6. But we can say approximately equal to 1 and approximately equal to 1.5. Okay, you can see the bend in the curve where the current starts saturating, or becomes like a flat line, constant line. And from our applied VGS, if we subtract that voltage, we obtain the threshold voltage VTN. So 3.5 volts, 4.5 volts applied VGS, overdrive voltage 1 volt or 1.1 if you will. Then your excess voltages, your threshold voltage is 3.5 volts. You apply 5 volts, overdrive is 1.5, Threshold voltage is 3.5. Threshold voltage, of course, is a function of the physical design geometry and the doping profile. So that should not change. That is the voltage that is required to set up the channel. Okay. So once you fabricate a device based on the design, the threshold voltage is not going to change. That should remain constant. So 3.5 volts. We can also extract some information from the transfer characteristic. Transfer characteristic, I believe we spoke about this a little bit for the BJT also. Is showing you a plot of ID as a function of input voltage VGS. How is the input being transferred to the output? Okay, hence transfer characteristic. So input would be the gate source voltage VGS and the output would be the drain current ID. And from there, we obtain, or we can link that to one of the most important quantities for a MOSFET, transconductance GM. Ohm's law, V equals IR. R is V over I. Inverse of resistance is conductance G, which is I over V. So transconductance is transfer conductance. How is the input being transferred to the output? So it's a ratio of the output current to the input voltage. So change in output current as a function of change in input voltage, delta ID over delta VGS at the operating point, of course. An important parameter, transconductance GM. Not just for MOSFETs, it's there for BJTs also. And based on the device, based on the circuit, based on our application or system or our analysis, there are multiple formulae, multiple equations that we can use, 3 of which are shown here. Okay. All 3 forms find applications in many different circuits. Excuse me. Okay. And this then goes into device dimensions and KN. Let's see. Oh, power dissipation. Kind of obvious. We don't want current exceeding the device limits. And let's see. Nope. Okay. All right. So this is where we stopped in the earlier section. And so this is where I'm going to stop for this section also. We'll end class here today. We'll pick up here again on Wednesday.